Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. Today we will discuss chapter 3 for this course, which is solid liquid interface, which is a very important topic in interfacial chemistry. So this topic explains how molecules in a liquid interact with a solid surface, especially through a process called adsorption. So understanding this is important because it is widely used in many real-life applications such as environmental treatment, industrial processes, and separation techniques. Before we go further, let's look the examples of application of the solid liquid interface. As here we have ink and pigment dispersion. So when we print using a printer, the color we see comes from very small particles known as dyes or pigments. So the key difference between these two is their interaction with the solid surface. In the case of dyes, the particles dissolve completely in the liquid, similar to how sugar dissolves in water. So as a result, the dye molecules are evenly distributed throughout the solution. In contrast, pigments do not dissolve in the liquid. Instead, they remain as small solid particles that must stay dispersed in the liquid, similar to sand in water. So during printing, the solid surface, such as paper or a coating material, can selectively absorb pigment particles, allowing them to stick and form stable color, while dye may remain in the liquid phase or penetrate differently depending on their interaction. Okay, interaction between the dyes and the solid surface. So this selective absorption is crucial in applications like printing and ink formulations, where we want the pigment to first adhere strongly to the surface and then remain uniformly distributed, and most importantly is produce a stable and high quality color output. So this is why understanding absorption behavior is very important in designing efficient inks, coatings, and pigment dispersion. Alright, so let's look at more applications of the solid liquid interface in real life. Okay, first consider soil wetting. Okay, when water enters the soil, how wet it spreads depends on the interaction between the water and the soil surface. Okay, as shown here, water behave differently in different types of soil. Okay, in clay, water spreads slowly. In loam, it shows moderate penetrations, and in sand, it penetrates quickly. So these differences arise from variations in surface properties, pore size, and the interaction between water and the soil. Therefore, interfacial chemistry plays an important role in controlling how easily water wets and move through soil. Okay, next, let us consider chromatography. Okay, specifically paper chromatography. So in this technique, the color from leaf separates into different bands. This occurs because each component interact differently with the solid surface, which is the paper, and move at different speeds with the solvent. So components that interact strongly with the surface move more slowly, while those with weaker interactions move faster. So thus absorption at the surface controls the separation process. Okay, finally, let us look at lubrication. So in mechanical systems, oil is used between moving metal surfaces. So the lubricant is used to form a thin layer on the surface through absorption. So this layer reduces frictions and prevents wear and damage. Okay, without this interfacial interaction, the surfaces would come into direct contact and grind against each other, leading to damage. Okay, now consider agriculture, okay, particularly soil wetting and pesticide application. Okay, when water or pesticide are sprayed onto crops, so they need to spread properly over the leaf or soil surface. So if the liquid does not wet the surface effectively, it will form a droplet and may roll off, leading to wastage. On the other hand, good wetting allows better spreading, improved absorption, and more effective pesticide action. So this behavior depends on how the liquid interacts with the surface, which is governed by interfacial chemistry. Okay, next, let's us consider the application of paint. So when paint is applied to a wall, it must spread evenly and at highest strongly to the surface. So this occurs due to absorption between the paint molecule and the wall surface. So if the interaction is weak, the paint will not adhere properly and may peel off or form an uneven coating. So therefore, interfacial interaction play a key role in determining the quality and durability of the paint. Okay, finally, let us look at a more advanced application, which is enhanced oil recovery. So in this process, oil is trapped within a very small pore in underground rock formations. So the main challenge is how to extract this trapped oil efficiently. So by applying interfacial chemistry, we can modify the wettability of the rock surface and reduce the interaction between the oil and the rock. So this allows the oil to detach more easily from the surface and flow through the pore. So as a result, adsorption and surface interaction are used to improve the efficiency of oil extraction. Alright, so let us understand the adsorption model. Okay, so in this system, we have a solid surface, which is here, and a liquid phase, which is here. So the boundary between these two phases is called the interface, right? So an important point to note is that this interface is not just a simple line. Instead, it is a thin region where special interaction occur. So the molecule in this region behave differently from the molecules in the bulk liquid and also differently from those inside the solid. Okay, so when molecules from the liquid come close to the solid surface, they experience various forces such as attraction, repulsion, and electrostatic interactions. So as a result of these forces, some of the molecules will attach to the surface. So this process is known as adsorption. Okay, to make this easier to understand, you can think of the surface as a sticky wall and the molecules in the liquid as small balls. So when these balls come close to the wall, some of them will stick to it. So this sticking occurs only at the surface and not within the bulk of the material. So it is important to remember that the interface is extremely small. Typically, only a few molecules stick. However, despite its small size, it plays a very important role in controlling many processes, such as adsorption, wetting, and separation. Okay, so let's understand more about the adsorption model by focusing on what happens at the interface. Okay, when molecules approach the solid surface, specific interaction occur between the molecules and the surface. So these interactions are not random. In fact, they can significantly change the properties of the liquid near the surface. So at the interface, properties such as the density, the dielectric constant, and even other physical or chemical characteristics can become different from those in the bulk liquid. So as a result, the liquid near the surface behave differently compared to the liquid farther away. Okay, so based on these interactions, we can observe two types of adsorption. So in the case of positive adsorption, okay, more molecules accumulate at the surface. So this means that the concentration at the interface is higher than the concentration of the liquid in the bulk solution. So this indicates that the molecules are attracted to the surface and tend to remain there. In contrast, negative adsorption occur when fewer molecules are present at the surface. So in this case, the concentration in the bulk is higher than the concentration of the liquid at the interface. So this suggests that the molecules are repelled from the surface. Okay, in summary, the interactions at the interface can either attract or repel molecules, okay, leading to different concentration distribution and different adsorption behavior. Okay, let's look at this diagram to better understand adsorption at the interface. Okay, in the case of A, Okay, we are absorbing a normal solution that does not contain strong surface active molecule. So in this situation, the molecules are mostly evenly distributed throughout the liquid. Okay, and only a small number of molecules are absorbed onto the surface, which is represented by this black circle. So as a result, the amount of absorption is low and the concentration at the surface is only slightly higher than in the bulk solution. Okay, in the case of B, okay, the situation is different. Here we have surface active molecules, okay, which are molecules that tend to move toward and remain at the surface. Okay, you can see here there are many black oval molecule at the surface. Okay, examples of such molecules include surfactants and detergents. Okay, so these molecules strongly absorb onto the surface, okay, leading to a much higher accumulation at the interface. Okay, because of this strong absorption, a large number of molecules gather at the surface, resulting in a high concentration at the interface compared to the bulk liquid. So this lead to an important concept known as excess solute concentration at the interface. This means that the concentration of molecule at the surface is significantly higher than the concentration in the bulk phase. Okay, in summary, the presence of surface active molecules greatly increase absorption and creates a noticeable concentration difference between the interface and the bulk solution. Now, let's look at this diagram to understand the absorption in a more quantitative way. Okay, so in this diagram, we have a solid surface with an irregular shape and a liquid phase containing solid molecules, which are represented by the black dots. Okay, you can observe that many of these molecules are concentrated near the surface. So the key idea here is that even though the solute is dissolved in the liquid, some molecules prefer to move toward the surface and remain there. So as a result, a layer of molecules form, effectively coating the solid surface. So an important observation is that the concentrations of molecules is higher near the surface and lower in the bulk liquid. So this difference in concentration is what we describe as absorption at the interface. So this occur because of the interaction between the solid surface and the solute molecules. When the attraction between them is strong, okay, more molecules accumulate at the surface, leading to a stronger absorption. Okay, when we refer to a quantitative understanding, we mean that we are interested in measuring how many molecules are absorbed and how the concentration changes near the surface. So these measurements form the basis for absorption models such as the Langmuir isotherm and the Friendlich isotherm, which we will discuss more later in this chapter. Now we move from understanding the concept of absorption to something more quantitative. Okay, at this stage, we are studying how a surfactant, okay, which is the solute, interact with the solid surface through absorption. The important questions we want to answer is how do we measure this absorption? Okay, so first we consider the amount. Okay, the amount absorbed. This refers to how much surfactant is absorbed per unit mass or per unit surface area of the solid. This parameter helps us understand how strongly the surface can hold the molecules. Okay, next we examine the relationship between the concentration and surface coverage. In other words, we ask what concentration of surfactant is required to achieve a certain degree of surface coverage. Simply put, we are trying to determine how much solute is needed to effectively cover the surface. Okay, another important concept is surface saturation. Okay, here surface saturation. So at a certain concentration, the surface becomes fully covered with absorbed molecules. Okay, beyond this point, no additional molecule can be absorbed, and this condition is referred as a surface saturation, or we call as monolayer absorption. Okay, we also need to consider the orientation of the absorbed molecule. Okay, the molecules can arrange themselves in different ways on the surface, such as laying flat or standing vertically, or adopting a head-tail orientation in the case of surfactant. So this arrangement influence how the surface behave and interact with its surrounding. So in addition, adsorption can affect the properties of the solid surface. For example, it can change the wettability, surface energy, and even the reactivity of the material. Finally, it is important to note that in most adsorption model, we assume that the temperature and the pressure remain constant. So this allows us to focus primarily on the effect of concentration on the adsorption process. Alright, so let's pause here for a short exercise. Okay, I would like you to try this on your own. Okay, in your own words, please explain what is meant by positive adsorption and negative adsorption. Thank you. Okay, now let's move one step further in our discussion. Okay, so far we know that adsorption depends on the interaction between molecules and the surface. So the next important question is, what controls how strong this adsorption is? Okay, the answer lies in the nature of the solid surface. So this is very important factor because it determines both the manner, which refer to how adsorption occurs, and the extent, okay, which refer to how much adsorption takes place. Okay, first let's us consider non-polar or hydrophobic surface. So this surface do not interact well with water and are therefore described as water hating. A common example is polyethylene, which is a type of plastic. So on these surfaces, on this surface, water does not spread easily and tend to form droplet. Okay, as a result, the adsorption of polar molecules on such surface is generally weak. Okay, next, we look at polar surface. Okay, polar surface but do not possess strong surface charges. Okay, means the surface is polar but do not have charge. Okay, so this surface are able to interact with polar molecules, including water. But the interaction is not as strong as in charged systems. Okay, example of such materials include polyester and natural fiber like cotton. So on these surfaces, liquid tend to spread more easily and adsorption is more favorable compared to non-polar surfaces. Okay, if you observe the diagram here, okay, you can clearly see the difference. Okay, on one type of surface, the liquid form a rounded droplet, indicating poor wetting. On the other surface, the liquid spreads more, indicating better interaction between the liquid and the solid. Okay, in summary, okay, the key point to remember is that the nature of the surface controls the strength of interaction between molecules and the surface. So this directly affect how much adsorption occur and how the liquid behave on the surface. So different types of surfaces will therefore result in different adsorption behavior. Now let us look at the third types of surface, which is strongly charged surfaces. So this surface contain charged site, okay, which can be either positive or negative. And a common example of such material is metal oxide. So because of the presence of these charges, okay, at the surface of the solid material, so the interaction between the surface and the molecule in the solution becomes much stronger compared to non-polar and neutral polar surfaces. Okay, when a surfactant approach a charged surface, okay, so this molecule we call as surfactant. Okay, when a surfactant approach a charged surface, so the head group of the surfactant is attracted to the surface, okay, through electrostatic force, okay, here. So as a result, adsorption becomes much more significant. Okay, if you observe the diagram, you can see how the molecules arrange themselves on the surface. Okay, first at low concentration, okay, at low concentration coverage, only a small number of molecules are attached to the surface. As the concentration increases, okay, more molecules begin to absorb and they start to form a more organized layer. Okay, at higher concentration, okay, the surface can become densely packed and the molecules may even arrange themselves into structured layer depending on their orientation. Okay, this shows that on charged surfaces, okay, adsorption is not only stronger but also more organized and structured. So the key point to remember is that electrostatic interaction play a major role, leading to higher adsorption and more stable surface coverage. Therefore, compared to non-polar and weakly polar surfaces, a charged surface generally exhibits stronger and more extensive adsorption behavior. Alright, before this slide, I have mentioned surface active agent or surfactant. So what are surfactant? Okay, surfactants are usually organic compound that are described as amphiphilic. Okay, so this means that they contain two different types of group within the same molecule. Okay, on one part of the molecule is hydrophilic, okay, which means it is water loving, and this is known as the head. Okay, so the other part is hydrophobic, okay, meaning it is water hating, and this is known as the tail. Okay, because of this unique structure, surfactant behave in a specific way when placed in a system containing water. Okay, let's imagine we have water system, we have water, and we put in the surfactant molecule. So what will happen? So the hydrophilic head, which is water loving, tend to interact with water. Okay, while the hydrophobic part, okay, which is water hating, tries to avoid water. So as a result, the surfactant molecule tends to arrange themselves at interface, okay, such as the water-air interface or the solid-liquid interface, where the head part will interact with water and the hydrophobic part will away from water solution. So at the interface, surfactant absorb strongly, okay, meaning they accumulate at the surface. So this absorption reduce the surface energy, which makes the system more stable and allows liquid to spread more easily. Okay, the key point to remember is that surfactant contains both water loving and water hating part, and this dual nature allows them to absorb at interface and modify surface properties. So actually, we are going to learn more about surfactant in the next chapter. Okay, so let's go back to non-polar or hydrophobic surface. Okay, so this type of surface do not interact well with water and are therefore described as water hating. Okay, if you look at the diagram, you can see that the water droplet forms a large contact angle here. Okay, a large contact angle which is greater than 90 degrees. So this indicates that the liquid does not spread easily on the surface, which is a characteristic of hydrophobic materials. Okay, next, let us consider how surfactant absorb on non-polar surfaces. Okay, when a surfactant approach a non-polar surface, so the interaction is mainly due to dispersion force, okay, also known as van der Waals force. So these are relatively weak interaction compared to electrostatic forces. Okay, because of the surface is non-polar, so the hydrophobic tail of the surfactant has a stronger affinity for the surface, which is non-polar likes non-polar. Okay, so while the hydrophilic head here tends to remain in contact with the water. So as a result, the surfactant molecules may arrange themselves with their tail interacting the surface and their heads facing outward into the liquid. So however, since the interaction is relatively weak, the overall absorption is not very strong, and the surface coverage may be limited compared to polar or charged surfaces. So the key point to remember is that on non-polar or hydrophobic surfaces, absorption is mainly driven by weak dispersion force. Alright, so let's discuss further how surfactants absorb onto non-polar or hydrophobic surface. So in an aqueous solution, the orientation of the adsorbed molecule is very important. Okay, because the surface is non-polar, so the hydrophobic groups of the surfactant tend to interact with the solid surface. Okay, why the hydrophilic groups are directed toward the aqueous phase or the water. Okay, if you observe the diagram, okay, here, you can see how the arrangement of the molecule changes as adsorption increases. So at the beginning, when the surface coverage is low, the surfactant molecule may lie flat on the surface, forming what we call as a flat trains. Okay, so if you see here, so the hydrophobic part of the surfactant is absorbed to the non-polar surface, while the hydrophilic head of the surfactant is pointing outward, interact with the water solution. Okay, so as more molecules are adsorbed, they begin to form a structure such as loops or L-shaped arrangement. Okay, this one, where we increase the concentration of the surfactant in the solution. Okay, and then at a higher adsorption level, okay, here, so the molecules start to stand more vertically with their hydrophobic tail attached to the surface and their hydrophilic heads pointing outward into the solution. Okay, eventually, the surface becomes fully coverage, forming a saturated monolayer. Okay, so this progression from the flat, okay, to the vertical orientation shows how the structure of the adsorbed layer becomes more organized as the amount of adsorption increases. So the key point to remember is that on non-polar surface, okay, surfactant molecules orient themselves in a way that maximize interaction between the hydrophobic part and the surface, while keeping the hydrophilic head in contact with water. So this arrangement leads to the formation of a stable adsorbed layer at the interface. Okay, so now let us move to polar uncharged surface. Okay, in modern technology, many materials that are produced have polar surfaces. But importantly, these surfaces do not carry strong electrical charges. Okay, so means the surface is polar but do not have charge. Okay, if you look at the diagram, you can see that the water spreads more on this type of surface, forming a smaller contact angle. Okay, this one, smaller contact angle, less than 90 degrees. So this indicates that the surface is hydrophilic, meaning it is a good interaction with water. Okay, even though these surfaces are polar, they do not have discrete surface charges. Okay, therefore, the interaction between the surface and molecule in solution is stronger than in polar system, but weaker than in fully charged surface. So it is in the middle. Okay, so example of such materials include synthetic polymeric materials as well as natural fiber like cotton, which we have discussed before. Okay, in terms of adsorption, surfactant molecule can still interact with the surface through dipole-dipole interactions or hydrogen bonding, okay, depending on the system. So as a result, adsorption on polar uncharged surface is generally moderate, okay, meaning it is stronger than on non-polar surfaces but not as strong as on charged surfaces. Okay, so the key point to remember is that polarity improve interaction and wetting, but without surface charge, the adsorption is not as strong or highly structured as in charged system. Okay, now we focus on the mechanism of adsorption, okay, for polar uncharged surface. Okay, so for this type of surface, the adsorption mechanism is more complex compared to non-polar surfaces. This is because several types of intermolecular forces can operate simultaneously. Okay, so the first type is dispersion force, okay, which are weak interactions present in all systems. In addition, we have dipolar interaction, okay, which occur between molecules that have permanent dipole. Okay, we may also have hydrogen bonding, okay, especially when the molecules or the surface contain functional groups such as hydroxyl or amine groups. And then another possible interaction is acid-base interaction, where electron donor and acceptor site interact with each other. Okay, because multiple forces can be involved at the same time, the overall adsorption behavior depends on which interaction are dominant in the system. Therefore, the key point to remember is that adsorption on polar uncharged surface is governed by combination of different intermolecular forces, making the mechanism more complex and system dependent. Alright, so let's further understand adsorption on polar uncharged surfaces by comparing the types of interaction involved. Okay, on one hand, okay, if dispersion force predominate, so the behavior is quite similar to what we observe for non-polar surfaces where the interaction are relatively weak. Okay, on the other hand, okay, if polar interaction dominate, the situation becomes different. So in this case, the orientation of surfactant molecule changes. So the hydrophilic head groups tends to interact strongly with the polar solid surface, so it will attach to the surface. At the same time, the hydrophobic tail will arrange itself away from the surface and extend into the aqueous phase. So let's pause for about 2 minutes activity. So I would like you to think about this question. How do you think the surfactant molecules will arrange themselves on a hydrophilic or polar surface? So try to describe the orientation of both the head group and the tail group. Alright, so have you tried the activity? Okay, so let's discuss the answer. Okay, let's recall again. Okay, if the dispersion force predominate, then the adsorption behavior is quite similar to that observed for non-polar surfaces where the interaction are relatively weak and less specific. However, okay, if polar interaction dominate, so the situation becomes different and more structured. So in this case, the orientation of the surfactant molecule is influenced by the polarity of the surface. So the hydrophilic head group of the surfactant tends to interact strongly with the polar solid surface, so it attaches directly to the surface. At the same time, the hydrophobic tail is oriented away from the surface and extend into the aqueous phase. Okay, if you look at the diagram here, you can clearly see this arrangement. Here we have the hydrophilic head is positioned at the surface, okay, interacting with polar groups such as hydroxy groups, while the hydrophobic tail extend outward into the solution. So this type of arrangement is a result of specific interactions at polar surfaces such as dipole-dipole interaction or hydrogen bonding. So the key to remember here is that on polar uncharged surfaces, adsorption behavior depends on which types of interaction dominates. So when polar interaction are stronger, so the surfactant molecule form a more organized and directional arrangement like this one, with the head attached to the surface and the tail pointing into the liquid. Okay, so this leads to a more stable adsorb layer compared to system dominated by only a weak dispersion force. Let's move to the final type of surface, which is surfaces having discrete electrical charges. Okay, so these surfaces contain clearly defined positive or negative charge site, and this significantly affect how adsorption occurs. Okay, so in this case, the dominant interaction is charge-charge interactions, okay, also known as electrostatic interaction. Okay, compared to the previous surfaces, this type of interaction is much stronger, okay, which leads to stronger adsorption of molecule onto the surface. Okay, when surfactant molecules approach a charged surface, the oppositely charged head group is strongly attached to the surface. So as a result, adsorption becomes more significantly and the molecule can form a more compact and highly organized layer. Okay, so if you observe this diagram, okay, you can clearly see how the surfactant with negatively charged head is attached to the positively charged surface solid material. Okay, and then you can also see, okay, how the molecule gradually arrange themselves from low coverage, okay, to a densely packed structure as the concentration increases. Okay, so in the first diagram here, if we have low concentration of surfactant in the solution, and then when we increase the concentration of the surfactant in the solution, so how the surfactant is densely packed, forming a packed structure, okay, on the surface of the solid material. Okay, however, one important point to note is that this type of interaction is very sensitive to external conditions. Okay, for example, changes in pH can alter the surface charge. Okay, while the types of electrolyte present can influence how strong the electrostatic interaction is. Okay, therefore, the adsorption behavior on charged surfaces can vary significantly depending on the surrounding environment. Okay, so the key point here is that electrostatic interactions dominate on charged surfaces, leading to stronger, more structured adsorption, but the system is also more sensitive to changes in conditions such as pH and electrolyte compositions. Alright, so let's take a deeper look at adsorption on surfaces having discrete electrical charges. So this type of adsorption is considered the most complex, okay, because it involves a strong electrostatic interaction and occurs in several stages. So let's go through the diagram step by step. So first, in stage A here, so we have the native surface, okay, which already carries a charge. So in this case, we have a positive charge of solid surface, okay, and then around it, there are ions distributed in the solution, but no significant adsorption of surfactant has occurred yet. Okay, let's move to stage B here. So here we have ion exchange. Okay, so the surfactant molecules, which is represented by this diagram, okay, which carries an opposite charge, start to replace the ion that were originally near the surface. Okay, so when we have a positive charge surface, so we have surfactant that carries negatively charged at the head. So this is driven by electrostatic attraction, okay, between the surfactant head group and the charged surface. Okay, and then in stage C here, okay, we observe ion pairing. Okay, at this point, more surfactant molecules accumulate at the surface, and their charge begins to neutralize the surface charge. Okay, imagine when you have positive charge, and then when you have surfactant which is negatively charged, so it start to neutralize the charges, right? Okay, so as a result, the zeta potential decrease and tends towards zero. And finally, in stage D here, so we reach complete charge neutralization. Okay, so the surface charge is fully balanced by the absorbed surfactant molecules. So at this point, the zeta potential is zero, which is also known as the zero point of charge, or ZPC. Okay, ZPC when the zeta potential become zero. Then these progressions shows how adsorption on charged surfaces involve from simple attraction to a fully neutralized and structured surface layer. So the key to remember here is that adsorption on charged surfaces involve multiple stages like this one. Okay, including from ion exchange, and then ion pairing and charge neutralization, okay, making it more complex but also more controllable through factors such as pH and electrolyte concentration. Alright, so let's summarize the mechanism of surfactant adsorption on surfaces with discrete electrical charges. So in system where the surface already has counter ion, okay, counter ion means the ion that have different charge with the solid surface. Okay, let's say in our previous example, we have positive charge, so the counter ion is negative ion. Okay, so the adsorption process typically occur in three main stages. Okay, so the first stage, the adsorption occurs mainly through ion exchange process. Okay, ion exchange process. So in this stage, the counter ions that are originally attached to the surface are displaced by the surfactant molecules. Okay, however, even though this exchange take place, the overall electrical characteristic of the surface or its surface charge remain essentially unchanged. Okay, and then in the second stage, we have ion pairing. Okay, ion pairing begins to occur. So at this point, the surfactant molecules start to interact more strongly with the surface charges, okay, leading to a reduction in the overall surface charge. So as a result, the zeta potential decrease and gradually approaches zero. Okay, and then in the final stage, okay, which is the third stage, okay, we reach complete neutralization of the surface charge. So here, the absorbed surfactant molecules fully balance the original surface charge. So this condition is known as the 0 point of charge or ZPC, okay, where all surface charges are effectively neutralized. So the key to remember is that adsorption on charged surface is a stepwise process, starting from ion exchange, followed by ion pairing, and finally reaching complete charge neutralization. So this is why adsorption on charged surfaces is considered the most complex, okay, but also the most sensitive to factors such as pH and electrolyte conditions. Okay, so before we move further, so can you try to answer this exercise, and we will discuss the answer together later. Thank you. Let's move on to the concept of adsorption affinity. So in this section, we are focusing on the theoretical treatment of adsorption from solutions. Okay, compared to gas adsorption, adsorption from solution is more complicated. So this is because in a liquid system, there are more components involved and more interactions taking place. So in gas adsorption, we usually consider only the interaction between the gas molecules and the solid surface. However, in solution, we must consider not only the solute but also the solvent. Okay, so this means that adsorption from solution involve a competition. Specifically, there is competition between the solute molecules and the solvent molecules for the available adsorption site on the surface. In addition, if the solution contains more than one component, for example, if there are two types of solutes, so there will also be competition among the different components of the liquid mixture for this adsorption site. Okay, if you look at the diagram, okay, you can imagine that both solute and solvent, okay, let's say the black circle here is the solute and the red circle here is the solvent molecules. Okay, they are both trying to approach and occupy the surface. Okay, however, only those with stronger affinity towards the surface will be preferentially absorbed. So the key to remember is that adsorption from solution is governed by competition interactions, making it more complex than gas absorption, where only one type of molecule is involved. Let's discuss more on the adsorption affinity in solution system. So in this case, the adsorption of a solute is not determined by a single factor, but is influenced by the competition between the solute and the solvent for the adsorption site on the solid surface. Okay, so if you look at this diagram, okay, you can see three important interactions labeled as A, B, and C. Okay, first A, here, A is represent the adsorption potential of the solute. Okay, potential adsorption of solute to the solid surface. So this describe how strongly the solute molecules are attracted to the surface. A higher value of A means the solute has a stronger tendency to absorb to the solid surface. Okay, second, we have B. Okay, B represent the interaction between the solute and the solvent, okay, which is related to solubility. So if the solute interacts strongly with the solvent, it tends to remain dissolved in the solution rather than moving to the surface. And then finally, third, we have C. So C represent the absorption potential of the solvent. Okay, so this indicates how strongly the solvent molecule themselves compete for the same absorption site on solid surface. So therefore, the overall absorption behavior depends on the balance between these three factors. So if the solute has a strong absorption potential and weak interaction with the solvent, it will preferentially absorb onto the surface. However, if the solute is highly soluble or if the solvent strongly absorb onto the surface, then absorption of the solute will be reduced. So the key to remember here is that absorption from solution is governed by competition, and the extent of absorption depends on the relative strengths of solute surface, solid solvent, and solvent surface interactions. Alright, so let's further discuss on absorption affinity. So the key idea here is that the ability of a solute to be absorbed depends on the potential difference between the solute and the solvent interactions. In other words, the absorption is not only about how strongly the solute is attracted to the surface, but also about how it compares with the solvent ability to interact with that same surface. So now let us consider two different situations. So in the first case, where the absorption ability of the solvent is high, so the solvent molecule will strongly compete for the absorption site. So as a result, the surface will be mostly occupied by solvent molecules and the absorption of the solute will be low. Okay, in the second case, where the absorption ability of the solvent is low, so the solvent molecules do not strongly compete for the surface. So this allows the solute molecule occupy the absorption site more easily, and therefore the absorption of the solute will be higher. So the key point here, the absorption depends on competition between solute and solvent, and the one with the stronger interaction with the surface will dominate the absorption process. Right, so let's discuss more on the first case. So here we have the absorption ability of the solvent is high. Okay, so this means that the interaction between the solvent and the solid surface, which is we denote as interaction C here, is much stronger compared to the interaction between the solute and the solid surface, which is interaction A. So as a result, the solvent molecule will preferentially occupy the available absorption site on the surface. Okay, because of this strong competition, fewer sites are available for the solute molecules. So therefore, the absorption ability of the solute will decrease, or in other words, it becomes limited. Okay, so let's look at the example given here. Okay, let's say we have a polar absorbent, okay, such as zeolite, and then we have polar solvent, which is water, and non-polar solute. So in this situation, the polar solvent interacts strongly with the polar surface through interactions such as hydrogen bonding and dipolar interactions. So this makes it very difficult for the non-polar solute to compete for the absorption site. So the final result is that the absorption of the solute is limited, mainly because the solvent has a stronger affinity for the surface due to its polar nature. Okay, here for the second case, so in this situation, the absorption ability of the solvent is low. So this means that the interaction between the solvent and the surface, which we denote as interaction C, is weak. So as a result, the solvent molecule does not strongly compete for the absorption site. So because of this reduced competition, so the solute molecules now have greater access to the surface. So therefore, the absorption of the solute will increase. Okay, let's look at the example given here. So here we have non-polar absorbent such as activated carbon, and non-polar solute such as polymer in a polar solvent, which is water. So in this case, the polar solvent does not interact strongly with the non-polar surface. So water molecules are not strongly attached to the surface and can be easily displaced. So this means this makes it easier for the non-polar solute molecule to replace the solvent at the surface and become absorbed. So as a result, we observe a high absorption ability of the solute in water. So this is because a lower absorption potential energy is required for the solute to replace the weakly absorbed solvent molecules. Now let's summarize what we have learned about absorption affinity by looking at the condition for effective absorption. Okay, so the key idea here is very simple. Absorption is most effective when the solute has a stronger interaction with the surface compared to the solvent. Okay, so let us look at the first case. So we have polar absorbent, a non-polar solvent, and polar solute. Okay, so in this situation, the polar solute can interact strongly with the polar surface through interactions such as dipole-dipole interactions or hydrogen bonding. So at the same time, the non-polar solvent interacts weakly with the surface. So the solute can easily replace the solvent at the surface, leading to effective absorption. Okay, now let us look at the second case. So we have non-polar absorbent, polar solvent, and non-polar solute. So here, the non-polar solute has stronger affinity for the non-polar surface through dispersion force. So meanwhile, the polar solvent does not interact strongly with the non-polar surface. So again, this allows the solute to displace the solvent and absorb onto the surface effectively. So if we refer back to the diagram, so again, A represents the interaction between the solute and the surface. B represent the interaction between the solute and the solvent, and C represent the interaction between the solvent and the surface. So for effective absorption, we want A to be strong and C to be weak. So the solute can successfully compete for the absorption site on the solid surface. So the important key point here. So the absorption is favored when the solid surface interaction is stronger than the solvent surface interactions, and when the solute is more compatible with the surface than the solvent. Now let us introduce an important concept known as Thorpe's rules, which helps us understand and predict absorption behavior. So the key idea of Thorpe's rules is based on polarity. So a polar absorbent tends to absorb polar absorbate strongly, while non-polar absorbate are absorbed more weakly. So conversely, a non-polar absorbent will preferentially absorb non-polar substances. So in simple terms, substances with similar polarity tend to interact more strongly with each other. So this concept also applies to the role of the solvent. So a polar solute will be strongly absorbed from a non-polar solvent because its solubility in that solvent is low. So as a result, the solute tends to leave the solution and absorb onto the surface. On the other hand, when the solvent is polar, the solute becomes more soluble and remains in the bulk solution. So therefore, the extent of absorption decreases. So this again highlights the importance of competition between the solute and the solvent for the absorption site. So polarity itself is related to the ability of molecule to form hydrogen bonding and dipolar interactions. So these interactions are stronger and more specific compared to non-specific dispersion force. So because of this, polar molecules are able to overcome weaker dispersion interactions and absorb more strongly onto compatible surfaces. So the key takeaway from Thorpe's rules is that Absorption is strongest when the absorbent and absorbate have similar polarity and when the solute is less stable or less soluble in the solvent. So when analyzing absorption behavior, always consider the polarity of the surface, the solute and the solvent, and these factors together determine the strength of absorption. Alright, so in this slide, it explains the assumption behind the Thorpe's rules. So the first assumption is that the absorption is limited to a monolayer only. So this means that only a single layer of molecule can form on the surface and no additional layer will build up on top of it. Okay, means there is no multi-layer absorption. So the second assumption is that the interaction between the solute and the solid surface decrease rapidly with distance. So in other words, only molecules that are very close to the surface will experience strong attraction and be absorbed. And then the third assumption is that the solute remains soluble once more than one layer is formed, meaning that after the first layer, the additional molecule prefer to stay in solution rather than to be absorbed to the solid surface. So because of these assumptions, we conclude that multi-layer absorption does not occur in this model, and then only a single monolayer of adsorbed molecule is considered. And then as shown in this diagram, so the surface is covered by one layer of molecule arranged side by side, forming a complete monolayer, and there is no multi-layer absorption for the liquid surface for the liquid molecule to the solid surface. Okay, also note that I here is represent the number of absorption layer. So when I equals to 1, it means only one layer is present, which is consistent with this model. So the key word here, the Thorpe's rule assume monolayer absorption with no further layer formation, and the absorption is mainly governed by interaction very close to the surface. Alright, so here some exercise that you can try to answer to test your understanding. So please try and we will discuss the answer together later. Thank you.